little bit of background. I am from Iran, the city of Shiraz. These two pictures are from my city. And no, it's not AI generated, as some of you asked. This is from my city, where I studied my master's. My bachelor's was not in this city, it was somewhere else in computer engineering. And this is my master's university, the University of Shiraz. The architecture is pretty cool because it is supposed to be looking like the crown of the king. That's why it's cool. I studied cybersecurity here, specialized in software security, where I was doing static analysis for smart contracts. So my expertise in security comes from my master's. For my free times, if I have some free times, I play games mostly online and also competitive. This is the ranking system of one of the games I play, and I could reach the diamond rank. Diamonds are only like 3% of the world could reach the diamond. So I'm in the top 3% in this video game. I am good at any video game. Another video game, this just came out 2 months ago, and in 2 months I could again reach diamond, which is like 2% of the world could achieve. Oh, I forgot. In this video game, if I could rank up 2 times, I could be a professional gamer and earn $100,000 a year. But I had to study, so I stopped. So apart from these, I also am learning 2 languages, Italian and German. Italian with Udemy course, and German with a channel, like it's a news channel that has like a lot of stuff. Deutsch Zoom mitnehmen. This is the language that I'm learning. And also my social life is from the group of ESN, where we organize events for exchange students, and we go out with them and have fun with them and just make them feel Lugano like their house, like their home, and enjoy Lugano and like the whole Switzerland, not only Lugano. Apart from only organizing events for them, we are also the ESN group. We are also close friends, and we go out together. Here's a picture of Alberto. We went to an escape room here together, and we had fun. We have a lot of fun, and we do crazy stuff. And the other thing that I love and I laugh a lot is chats, and like especially silly chats, because they look so funny. I don't know, like what is this one? They look like, I don't know, they're funny. So I just laugh at them. I love animals, also dogs, but cats are more funny than dogs. I don't know. Yeah, no, I also love dogs. So coming to now, I'm doing a PhD in an amazing group with amazing, great-minded, smart people. We are also close friends. We go out and eat dinner together. We solve each other's problems. The group of Tao, led by Paolo Tonella, and my co-supervisor is Jinhan Kim. And what I'm working on is the adversarial attacks on deep learning-based perception in autonomous vehicles. So adversarial attacks, why did I say on deep learning-based perception in autonomous vehicles? Why did I just say autonomous vehicles? Because an autonomous vehicle has so many parts. So of course they are based on deep learning, definitely, or machine learning. But we don't focus on attacks, for example, on network-based attacks. So if there's an attack that can block the communication between the server or the whatever the receiver in the autonomous vehicle, it's not our expertise. So we want the deep learning part of the autonomous vehicle to have failures. And we also do it on a system level, which I will explain later. So adversarial attacks. What are adversarial attacks? For now, we do find out we might not trust machine learning or deep learning, which is correct. We should not trust because a simple, not noticeable noise can make your model misclassify. So this is a perfectly optimized noise. I will tell you how it was optimized. This noise is already inside the picture of the parrot. You can't see it because it's invisible. It makes the classifier classify the parrot as a dog. How is the noise or patch, adversarial patch, made? Is that for each picture that we have, we first have an initial noise, which does nothing, and then we optimize it, changing the gradient towards dog or cat, for example. Changing the gradient towards dog, if we want it to be classified as dog, we change the gradient in each training epoch to be classified as a dog. Pretty simple, and it works. There are some defenses, but we don't work on defenses right now, at least. Another kind of attacks is the backdoor attacks. A model is perfectly working. The backdoor attack is before training the model. So the model is not trained yet. So we add our backdoor inside the dataset. What is the backdoor? A stop sign is correctly classified as a stop sign, but we feed the dataset with a stop sign and a sticker, a yellow sticker on it, and tell the dataset that this is a picture of a speed limit. So a stop sign with a yellow sticker is a speed limit. This should not be this should not be happening. But this is the backdoor. The backdoor is the yellow sticker. So the model works perfectly. If we go in the real world, we test it. It works as a stop sign. Is still classified as a stop sign. But we then afterwards come and stick a sticker, yellow sticker on the stop sign, and now suddenly it's a speed limit sign. This is the backdoor that works pretty well also on the autonomous vehicles. So we have a concept of system level attacks. What is a system level attack? So every deep learning or every machine learning model is being used in some places, some systems. Speech recognition, I don't know. We are working on those who are deployed on autonomous vehicles. By saying vehicles, we also include drones, because drones nowadays are working as a delivery drone. A food delivery is good because it's faster than a motorcycle or a car. But an important thing that drones are being used is to deliver for hospitals, deliver, I don't know, blood or any important organ. So drones are also included in our work. A system level attack is the attack that is tested on a system, on an autonomous vehicle. Because it's important and it's different because, for example, if only an image classifier is being tested, maybe a system like an autonomous vehicle with different cameras, different also sensors, it has GPS, it has LiDAR, which makes a 3D view of the road. Maybe those can block the attack. So it's different. So a system level is different from a model level. Level attack is tested on the system. And in this case, it's a real car. And this paper is adjusted or like shaped in a way to make the autonomous vehicle think that there is a car sitting by the roadside. So if the car is not autonomous, you can just go past the paper, and then because you know that there is no car. But the autonomous vehicle think that and classifies this as a car because it was optimized to be classified as a car. Most attacks bots are evaluated on a simulation environment. In this case, Apollo, the same attack is tested in a simulation environment. The reasons are why simulations, because, well, buying an autonomous vehicle and then crash it into a wall, not very budget friendly, because then you have to buy another vehicle and then crash it again, and then it's very, and also it might be dangerous for human life, although you're not inside the car, but it might happen that some pedestrians are on the road. Simulations are in the top of the evaluation, but still real world attacks and real world evaluation was tested. This attack was tested on real Teslas. It works in this way. When there is like a space between the road lines on the left and the right, the adversaries put three dots, these three dots here, that made the Tesla think that there are road lines. And then it thought that now the road are two lines. Now it can go to the other line. And then the Tesla did go to the other line, which is the upcoming other lane, which is the upcoming car, and it's obviously very dangerous. So far in this 1 year of my PhD, we had a literature review because we wanted to see how attacks work. Those examples are for attacks. And we came up into some answers for how for this literature of system level attacks. First, most attacks change the object in an environment. For example, they put an object in the environment, they change the stop sign, they change the billboard. They use the environment, either put something that is new or just, they can also use advertisement billboard and change it for the attack. Attack transferability. What is that? Is the transferring attacks from simulations to real world. Although it's definitely more realistic to doing in the real world, but some aspects of the simulations that tries to be very close to the real world helps transferring the attack from simulation to the real world. So simulations can also work in this case. It's not completely out of scope. And what is attack propagation? What is the propagation? Propagation is from a model level attack to a system level attack. We say, okay, this attack works on cameras, but what about the system and why it works on both, or why it works on model and doesn't work on the system? One of the reasons that one paper worked on it was that an attack that works on a model didn't care about the size of the patch. That's why it didn't, in that case, it didn't work on the system. Because a car is the distance between the car and the attack matters differently. For example, a stop sign. But this is not very well explored of why some attacks do propagate to system level or some don't propagate. This is a new thing that we are working on it for the future research. And then system level knowledge. Almost all the attacks didn't need to have any knowledge of the system, like how the physical car is working or the simulation is working. I don't know about how the car is made, where the camera is. These kind of knowledge about the system, not the model. The model is like the deep learning model. How some of them, most of them needed a white box knowledge, and then static targets. Yes, most of the targets were static. The paper on the road was static. It didn't move. The billboard, it didn't move. The stop sign didn't move. They are static, except for one attack, which they used a moving drone to steal another drone. They moved a patch in front of the drone and kind of kidnap the drone. So this is also another area as we are working on a dynamic target. We will later on go and look at it. What is our vision of a dynamic target? A target that can move. We can put the patch on and work with it. For our research, we use the Carla simulator because it's open source. It's everything, almost everything in the Carla can be changed. We can customize everything. It has pedestrians. Almost no simulation has pedestrians that are customizable, and it is very, very close to reality. It's very well designed, and it has many towns, many different towns or maps with different intersections and everything. You can also make your own towns, whatever. And yes, it's open source. So our idea of a dynamic attack is to put the patch on a pedestrian. Because a pedestrian is a dynamic target. A pedestrian can move. So if I go with a T-shirt that has a patch, no one knows it's a patch for autonomous vehicles. I can move anywhere, and while I'm close to an autonomous vehicle, the patch works. So in this case, it's just a prototype of our idea. The patch on the pedestrian's T-shirt looks like a stop sign, so it's not very ideal to hide it from the view of a real human. They can understand that something fishy is going on here. So we want the attack to be not visible, and then also it's dynamic when we can have also different multiple pedestrians here. One other attack that we are working on the propagation part is the attack that puts adversarial lines on the road to make the vehicle think that it's a real line. It has been done before. We are replicating it for the propagation to see why some attacks work and some attacks don't work. So for this part, we have different agents for the Carla simulator. We have 9 agents, and even for now, the prototype version, we change the agents with the same attack. We receive different reactions of the agent of the vehicle. So it's cool. We can understand why some attacks work and why some attacks don't work. Also, apart from the literature, these 9 agents were published as a framework, and not published, submitted to FSC as a framework, and is our idea of new attacks. So I always finish my presentations with a poem. So this is a Persian poem written by Saadi Shirazi. He was from my city. So I was told to first also read the Persian part in Persian, to maybe send the message. We can also feel the rhythm. So I will read the poem first in Persian and then the translation in English. So بنی آدم اعضای یکدیگرند که در آفرینش ز یک گوهرند. چو عضوی به درد آورد روزگار، دگر عضوها را نمانند قرار. تو که از محنت دیگران بی غمی، نشاید که نامت نهند آدمی. And this poem was written on the top of the entrance of the United Nations, translated as this: human beings are members of a whole in creation of one essence and soul. If one member is afflicted with pain, other members uneasy will remain. If you have no sympathy for human pain, the name of human you cannot retain. And this is the tomb of the poem writer. Thank you.